All right, Peter, take it away.
All right, so welcome. This is C++20 in Chromium. This is going to be a four-part series, so over the next 4 weeks, I'm going to go over all kinds of facets of C++20. There's Go links for this and every other presentation. They all have the same structure, CPP20-Chromium-number. So if you want to get an advanced look at what I'm working on, you can sneakily look at the slides for upcoming meetings and then not have to attend. So in this series, C++20 became available in Chromium in late 2023, but we've actually had no talks on it that I'm aware of, and most probably you are not someone who keeps obsessively up to date on new standards and things we do in Chrome, so there may be things you're not aware of that could improve your code. So we'll go over all kinds of stuff that's new that you can use, how you can use it, why you'd want to, also some stuff you can't use and why you can't use it, and how you can improve that situation. And special thanks throughout this whole series to my two test audiences, at least one of whom is here. I think actually maybe both of them are here, but Devin and Stacy have graciously listened to earlier drafts of these talks as I've gone through them and provided valuable feedback. So they definitely get a share of the credit for any goodness in these talks. And then one other aside before I jump in, which is it's already 2025, and some of you might be thinking, why are we talking about C++20? That's an eternity ago. Why isn't this a talk on C++23 or C++26 or something like that? Well, the answer is we don't have those. We only have C++20 in Chromium, and there's no time frame for upgrading. And if you are hoping that we're getting it this year, the answer is, I don't know, probably not. The C++23 spec is done, it's published, and classically Chrome's time frame has lagged the publication about 2 years. So normally this year would be a good guess on when we get it. But right now, Chromium leadership is kind of like, this is not a priority for us. So therefore, nobody is working on this. It's not going to magically happen if we don't do it. And thanks to Matt Riley for posting Google's internal C++ plan, if you have access to that in the chat. Okay, so now with that out of the way, what is in this specific talk, the meat of it? We're going to go over comparisons. Of all of the changes in C++20, I suspect that this is probably going to touch the most places in Chrome, and we can greatly simplify a lot of those places using several of the features I'm going to go over. We can also improve the performance and the safety and the expressiveness of our code over the C++17 world we were living in. And then finally, we can make Benny from the Lego Movie very happy by using this brand new spaceship operator that I'm going to talk about. So if you get that reference, great. Pre-C++20 world. First, we're going to talk about defaulting comparison ops. And the motivation here is, let's say you have some comparable type, and you're trying to actually write your operator equal implementation for it. Well, ways to do that differ, but most likely you wind up with something ugly, and I'm posting here my particular ugly take on this. In what this does in short is it looks at your superclass and says, is that portion of myself equal? And then it looks at all of your members in order and says, are those members equal? And fundamentally, you have to do these things in some form, even if you don't use std_tie or whatever. This is clearly quite verbose. It's error prone. It's very easy to omit or copy paste error some of the things in the tie statement. This is a maintenance hazard. If you ever add a member, you have to go modify the implementation here, or it will be wrong silently and the compiler will not save you. So thankfully, C++20 gives us a much shorter, better, and safer way to do all of this, and that is defaulted comparisons. Writing equals default on your comparison operators will just magically do the thing you wanted. This works not only for operator equal, it also works for all the other comparisons and inequality operators. And it does exactly what the previous slide does. It compares all the base classes and then all the members in declaration order. So as long as your members are actually comparable, this just works and is great. And that's really all there is to defaulted comparison ops. It's that simple. Reversed comparison ops, not quite as simple. Let me give some motivation again for these. So here in my pre-C++ 20 world, I have decided to write a custom number-like type called betterInt because I'm writing it so it's better than the int that exists. And I've decided that I want to make it easy for people to port their use of the old busted int over to my cool betterInt class. So I give an implicit implicit constructor that lets people upgrade. And then I write a comparison operator against other better ints. Now, plausibly, people might want to compare against ints as well. And my assumption is, well, this should just work because if they compare against an int, it'll be implicitly converted up to a better int, and then we'll compare using the member comparison operator I've done. And in fact, that's exactly what happens for the first of the two calls that I have at the bottom. Unfortunately, it doesn't happen for the second of the two calls, which barfs with a compiler error. And the reason for this is because to find candidate operator equal functions, the compiler looks at free functions that take the two args that I've given, and then member functions on the left-hand side type. So it says, oh, the left-hand side is in this case, for the 0 is called, it's an int, and it says, well, is int like a class that has a comparison operator against better int? Clearly no. So it doesn't work there, and the call says no comparisons found. So to fix this, often the route that people encourage you to go, again, this is in the pre-C++ 20 world, is to make the comparison op a non-member and have it take two args, both of your class type. And this will allow the compiler to do an implicit upgrade of the int on either side to a better int and then find this as a candidate free function. Now, you might be saying, wait a minute, I thought you just said make it a non-member, but you wrote it up in the class. Well, if you're not familiar with this syntax, writing something as a friend function in a class actually makes it a non-member friend function. It's just that it's conveniently defined for you right there where everything else is instead of down below the class. So this is just some C++ syntax sugar. This isn't new in C++ 20, but it's not commonly used by some folks. So now that we've done this, our two calls work, is 0 and 0 is. Things are great. Well, then I read the Google style guide. And the Google style guide says, hey, you probably shouldn't have implicit conversions. You should probably make your conversions explicit. There's lots of discussion we could go into on that point, but I decide, oh, okay, I'd better make my conversion operator or my constructor explicit. So I do that, and now, unfortunately, my comparison with an int doesn't work. I try adding a friend function that takes an int as the second arg, and that makes the first call work, but the second one still doesn't work. And so the solution to this is you wind up with these horrible chains of every combinatoric pattern of, my class on one side and the other class on the other side. Heterogeneous comparisons in the pre-C++ 20 world are just awful. So clearly, by the time we've gotten to this point, we've written a lot of copy and pasted code, and we're very unhappy. What can we do? Well, C++ 20 gives us something called reversed comparison ops. In the C++ 20 world, I can take that class and go back to just my single member function for my heterogeneous comparison, and it somehow works, no matter which way I put the comparison, which side I put the int on. How on earth does this happen? How does that bool operator equal member function manage to get found for both is 0 and 0 is here? Well, the way this works in C++ 20 is that for certain kinds of operations, the compiler will first try at the call site, doing it in the order that you specified, and then the compiler will try reversing it and doing it in the opposite order from what you specified. Now, intuitively, this makes sense to us because we know that checking for equality is a commutative operation. Like equality of A equals B is the same as B equals A. That said, this kind of makes that requirement baked into the language. If for some reason you were writing obfuscated C code and using operator equal equal to do something else that wasn't commutative, this is probably going to break you, because it assumes that equal equals is actually modeling something like an equivalence relationship. It turns out you can still override this sort of thing, but please don't, because it will confuse the heck out of all of your readers. And I want to make it really clear that the way this works is by the compiler trying different rewritings of the call site. It is not by the compiler generating new reversed comparisons inside your class. The compiler is not adding anything to the class API. It's not auto-generating any code into the binary. All it's doing is changing the caller and trying to match by having the args be in a different order. This is special logic that only applies to certain comparison operators called primary operators. I will say a little bit more about that in a minute. But that means there's no binary size impact. There's no weird like API incompatibility worries. Call sites are just more likely to do what you want. And it means that any code that still used pairs of comparison operators for heterogeneous comparisons just work in C++20, because the compiler will always try what you wrote as the first thing. Similarly, we have something called rewritten comparison operators. This is based on a very similar principle of changing the call sites, but instead of changing the order of the args, we're going to change what operators are called. So if you want to support not equals pre-C++20, the way I've seen almost every piece of code everywhere in the world do it is by just negating the result of operator equals equals. This is pretty sane and works fine. It's slightly error prone, but it's okay. But in C++20, you don't even need to write not equals. Just writing equals is enough to be able to call not equals on your class. This is because not equals is called a secondary comparison operator. And secondary operators differ from primary operators in that all secondary operators have an associated primary that they can be rewritten in terms of. The primary operator for not equals is equals. So the way that this works on the compiler side is to compile a not equals b, the compiler will try what you wrote. Then it will rewrite the not equals as the negation of equals and try that. And then if that doesn't work, it will also apply reordering and try that. So there's lots of fallback here, but there's a strict order. And Julian asked, does it not try B not equals A? So in other words, like, why not try reordering the secondary operator? It turns out, no, it doesn't, and it purposefully doesn't for a reason. And that reason is that if we also supported reordering on secondary operators, we would introduce an ambiguity where you could have different behaviors from a reordered secondary versus like a reversed reordered primary. And it could be very confusing and lead to bugs. So this was not an oversight. The committee intentionally was like, no, we're not going to do that. The fallback path is strictly rewriting and then reordering. And once again, this kind of assumes that not equals is the negation of equals, which is an assumption that probably is intended to work everywhere, but maybe you overrode it for some strange reason. So we've talked some about equals and not equals, but equals and not equals are far from the only comparisons you can do. There's 4 other inequality operators, and I'm just going to use inequality here to refer to these 4, the less than and greater than, and the less than equal to, greater than equal to. Let's talk about how those fit into the picture. So to support these pre-C++20, you have 2 imperfect options. The first bad option you have, well, maybe not bad, but imperfect, is that you just define operator less than. This is kind of the most common route. If you've ever looked around code and you've seen people define anything more than equals and not equals, often they'll just define, like, say, equals and less than. And they'll say something like, oh, we need less than so we can stick this type in a map, or so that we can pass this to some algorithm that wants this. It's actually possible with just less than to synthesize an operator equals. So some people don't even define equals at all. And some algorithms only require you to pass a less than or less than like comparison predicate in. You can synthesize it the way that I'm showing in this auto-generated eq function, where you just say, well, if A isn't less than B and B isn't less than A, then they must be equivalent. So there's a problem with this. What happens if you have a set of elements where not all elements can be meaningfully compared against all other elements? And if you're wondering about an example of that, floating point is an example of that. Because not a number in floating point doesn't have meaningful comparisons with any other value. If you try to write not a number less than something else, you will get false, because the compiler has to return true or false. But you'll also get false if you compare it the other way. You'll also get false if you compare it to yourself. Any comparison of nan against anything else will fail. That means our auto-generated eq function is going to produce a very curious result, because it's going to say, well, nan is not less than 42, and 42 is not less than nan, therefore those two values are equivalent. And clearly that's not correct. So really there's a hidden prerequisite here that all of your element comparisons are actually meaningful, which is something that both C++ and mathematics call a total ordering over the set. Equals isn't the only operator that is often auto-generated from less than. We can also look at how another operator suffers from total versus partial ordering problems. Here are ways to try to auto-generate a greater than equals operator from less than. If we try the first route, just negating less than, this is broken without a total ordering the same way our eq was broken without a total ordering. But if we use the second version to try to work around that problem, then it requires that we've actually defined a working operator equal separately, and we aren't using an auto-generated version of that, or we're back to the same problem. And it's inefficient if we do happen to have a total ordering, like if we're working on ints, because it's doing two comparisons instead of just doing a single one, like we could, in theory, get away with. So the upshot of all of this is that when your functions only take a single comparator, or when you only define less than on your type, then trying to do any other form of comparison gives you the choice between sometimes broken and sometimes inefficient, which is not a choice that generally we like to have as programmers. So we get to the other route for supporting these, which is to actually write all of them and to try to write them all in correct and efficient forms, assuming those exist. The problem with this is, for one, it's verbose as heck, and it's very easy to screw these up by copy and pasting something wrong. But more importantly, this doesn't really help us when we're working with templated code that also has to work with things that took the other route and don't have all of these. If your template code just assumes you can use these comparisons, it immediately breaks with a lot of types out there. Or if you're trying to pass to an algorithm that takes one of those like single comparison op things, then it breaks. And many of the standard library algorithms are like that. So all this is a huge mess. How do we get out of this huge mess? C++20 gets out of this huge mess by introducing a new operator called the spaceship operator, or in longer terms, the three-way comparison operator. I find spaceship to be a much more fun term, therefore I am going to call it spaceship. And actually, spaceship is the term that a lot of the papers in the standard use too. So this is a blessed name. What spaceship does at the low level, you can kind of think of it a bit like strcomp, in that it does a comparison between two things and then returns you a value that is either is comparable against 0, and like if you say is it less than 0, that will be true if A is less than B. If it's equal to 0, that will be true if A is equal to B, and if it's greater than 0, A will be greater than B. Now, I've said that in this very circuitous roundabout way because the value it returns is not actually an int itself. So it's not returning an int that's less than 0 or greater than 0 or whatever. And I will get to what it returns a little bit later. But this doesn't initially seem very helpful. Like, why would you want to rewrite all of your code in terms of doing all of this horribly ugly strcompy kind of like comparison when we already know from experience that APIs like strcomp kind of suck to use and we don't want to call them? Well, you don't usually manually call spaceship. The key thing a spaceship gives you is that it is a primary operator for rewriting all 4 of the inequalities, which all serve as secondaries to it. So the only thing you usually do with spaceship is you define it in your class. And bonus, you can use equals default in most of your classes, so you don't even have to write the implementation of spaceship. You literally just say, hey, this class has a defaulted spaceship operator, and in most cases, that's enough to suddenly make your class comparable with all 4 of these other inequalities. Because spaceship is primary, it supports reversing. So not only can you like rewrite the other comparisons to it, but you can have them like reorder their args. And as with equals and not equals, this is again based on the assumption that all of your different inequality operators relate to each other kind of as we would expect. So I want to note here, spaceship is only primary for these 4. It does not give you equals and not equals. You can kind of remember this by noting that the spaceship has the little angle brackets on the sides. Michael, I will talk in a minute about how defaulting spaceship works. I will get to that. So it has these angle brackets on the sides, and that's your cue that it serves as primary for operators that have those angle brackets in them. If you want equals and not equals, you do need to write operator equal separately. So using spaceship, we can actually do something that is maximally efficient for total orderings, has minimal binary size, and manages to be correct for non-total orderings. And if you don't immediately see how, because I sure as heck didn't, then let's continue on. We need to take a side trip into the land of orderings. So all of the people who did mathematics stuff should perk up and then get very sad, because I'm probably going to use language in ways that math does not use it. Roger asks, can you talk a little bit about not using spaceship for equals and not equals? I will also get to that when I talk about equals and not equals with spaceship. So I'm sorry here that sometimes my terminology is going to vary a little bit from what mathematics does. I'm going to use things in the C++ way. But to define the word ordering, an ordering is just how some group of values behaves with some comparator. So, for example, you might have heard of a strict ordering. In C++, a strict ordering is an ordering where reflexive comparisons fail. I'm not going to talk more about that because we don't actually care about strict orderings today, so it's not important to me whether you know what a strict ordering is. We do care about several other types of orderings, though, so I want to talk about those. In some particular set, we can be in one of 4 different cases when we compare 2 different elements. We can have element A ordered before B, which we usually call less than, A is ordered the same as B, A is ordered after B, which we usually call greater than. And then that NaN case, A is not comparable to B, which we usually say they're unordered with respect to each other. And even within the ordered the same as, we can have two different cases there. We can have, they're the same as in terms of ordering, but they're still distinguishable, or they're not distinguishable. Think of this as like case-insensitive string comparisons. In this case, when you feed it the same word, but capitalized or not, they're ordered the same relative to each other, but they're still distinguishable to a reader. And in C++, distinguishable, technically in the standard, is defined as distinguishable via public const methods. Now, there's no way that the compiler can track whether two variables are distinguishable using public const methods. You're going to have to just do that as a programmer and make sure you don't break that. But if you run into cases in the language that use words like equivalent versus equal, that's the distinction they're making, is it distinguishable using public const methods? So the reason that I show this slide is because this basically gives us a mapping between the ordering phraseology and the operator phraseology. Ordered before is equivalent to less than. One is talking about the ordering and one is talking about the result of an operator or a specific operator that we're going to call. And this mapping between these terms is important, and it's going to pay off in a couple slides. Yes, Ellie?
Yeah, when you say two things are equal in this sense, presumably their addresses can still be unequal while they are equal, right?
Yes. So since distinguishable here means distinguishable via public const methods, you could have two elements at different addresses in memory that nevertheless are indistinguishable via all public const methods, and thus they would be considered equal and not just equivalent.
I see. Okay.
Thankfully, the equal versus equivalent is a little bit of a rat hole. So if that all kind of is like, what, to you as you're listening, then don't worry too much about it. That is not the main point I'm trying to make here. The main point is really just linking these orderings and operators together. So let's give an illustrative example of this. This is a case-insensitive function for which string comes first in a dictionary. And that lets us demonstrate all 5 orders. We have less than with no is less than yes, because no comes before in the dictionary. We have both equivalent and equal, that case sensitive versus insensitive comparing thing that I mentioned earlier. We have greater than because yes comes after no in the dictionary. And then we have unordered if you say, well, the empty string isn't a word, so it doesn't appear in a dictionary, so we can't say where it appears compared to the word yes. So those are unordered in this sense. So this would be how you would map these practically. Well, what orderings does C++ actually care about? The first question you ask in your set is, are there any unordered pairs? If you have no unordered pairs of elements, you have a total ordering. If there are some, you have a partial ordering. It's possible to have a set where nothing can be compared to anything else, but C++ doesn't even bother to give that a word because the whole context here was that we were trying to write comparison operators. And when you have things where you can't ever compare anything, then that's kind of not very interesting to us. So note that this whole like total versus partial is distinct from the math sense, where all total orderings are also partial orderings. C++ says, no, they're partitioned, like a partial ordering is distinct from a total ordering. Then are equivalent elements sometimes distinguishable from each other? If you can sometimes distinguish equivalent elements using that public const method test, then you have what's called a weak ordering. If they're always indistinguishable, then you have a strong ordering. So you can kind of think of this as like the strong ordering it actually separates all the elements out into distinct buckets that only contain one element each, and thus it's a like stronger separation of the elements from each other. A weak ordering is weak because some elements wind up in the same bucket as each other, so you don't get as much separation as with a strong ordering. And there are names for these. These are represented as distinct types. C++20 has 3 such types: partial ordering for anything that's not a total ordering, weak ordering, and strong ordering, which are both total orderings. Now, I don't find it very memorable to just look at a list of words like this, so I have created a flowchart for you so that you can decide whether my type falls in, which bucket. You go, oh, are all the possible inputs comparable? If not, it's a partial ordering. If yes, then you ask the second question about equivalent values being distinguishable, and you get either strong or weak ordering. This is mentally how I do things. Now, of course, memorizing this flowchart is still left as an exercise for the reader. Julian asks, why can't I have a weak partial order? You can. Partial orders can be both weak and strong, but it turns out that C++ doesn't care about the difference. So that's why it lumps all of them into the partial ordering bucket. And when it's returning things from different functions, these are the 3 buckets it cares about. Now, within each of these types, you have several objects. So, for example, weak ordering defines a compile time constant less object as an instance of that type. And types only have instances that make sense. So like partial ordering has an unordered object, but weak ordering doesn't have an unordered object because weak ordering is a strong order, and in a strong order, there are no unordered pairings between elements. Okay, this seems like we've gotten way off into the weeds with, like, I don't know, type theory or programming language design or math or something. Like, why have we spent all of this time talking about orderings and types and these instances and stuff? What good is it to have one of these instances? Well, what operator spaceship actually returns is an instance of an ordering type. So it doesn't return int, as I mentioned before. It returns something like weak ordering : less, or partial ordering : unordered. And then those types provide overloads for all the different comparisons of those instances against 0 that return true and false in all of the right different cases. So like less instances will all return true when you compare them as less than 0 or less than equal to 0 or not equal to 0. Now, this might not immediately click for you. That's okay, because it took a minute to click for me. But I'll show an example of how the compiler is transforming these things here. If you write A is less than B, the first thing that happens is the compiler transforms that using operator rewriting into the primary operator, which is A spaceship B less than 0. The second thing that happens is that it actually executes A spaceship B, and it gets back some instance of an ordering object. In this case, my A spaceship B happens to return weak ordering less. Then it calls the overloaded weak ordering operator less than function with less, which is implemented as this comment I have here that says less than is true if this is less. And that returns true. The result of all of this is that when A is ordered before B per spaceship, calling A less than B ends up returning true. So you get the implementation of all of these comparison operators out of a single thing that actually implements orderings. And that in turn means that we can write something that's correct for non-total orderings, because all it has to do in that case is return the partial ordering unordered object. That unordered thing, in turn, is going to cause all of the comparisons to fail. So it's going to return the right result for us for our whole NAND versus 42 comparison. So here's an example of me manually writing a spaceship operator with a simple key value pair class. So I've got my class C. It's got a key and a value stored in it. There's also a public accessor that gets the value off of it. I don't give people access to the keys. And then there's a spaceship operator that tries to compare two instances of these class ordered by the key stored in the class. So, quiz for the readers. Yes, this is time for you to open your mic and speak up. What other orderings could I have written for the spaceship operator return type, and why should I have picked weak ordering instead of the other two? Michael writes, it's distinguishable. So I'm going to assume by that you mean this should be a weak ordering rather than a strong ordering, because sometimes you can have, yes, as Julian says, the same key, but with distinct values. And because there's a public const accessor that gets the value, you might have things that are ordered the same that are distinguishable. So, yep, that's several people have cottoned on to. That's why this shouldn't be a strong order. Why shouldn't this be a partial order? Yes, so Julian and Robert have mentioned this. Elliot, were you going to give one of those? Or
Yeah, I was going to say the same thing.
Yep. So the key here is that since we're ordering by int and all ints are comparable, ints are a strong order. Therefore, this thing is a strong order. And yes, other people have noted that if the value was included in the comparison, then this could be I keep saying strong order when I mean to say total order. Sorry. So yes, this is a total order because ints are a total order. Yes, Ellie.
Suppose this value method didn't exist, and I had written this therefore using a strong ordering because my instances of C were not distinguishable using any public const method, right?
Correct.
So suppose I did that. Then later on, I were to add this value method, and I now have instances of C that are distinguishable using a public const method, but I still have accidentally defined the spaceship operator's returning a strong ordering.
Yes.
What happens to me?
So this is a really good question. If you get the ordering class wrong, one of two things will happen. Either your returned ordering is more conservative than reality, or it's less conservative than reality. In this case, your ordering is less conservative than reality because you're saying that you have a strong ordering, but you actually only have a weak ordering. I don't think for that specific thing that probably anything is going to go wrong. You may mislead some readers. More likely, you will fail some constraints somewhere in like a ranges thing. And I have to talk more about constraints in next week's talk. But the upshots are usually either suboptimal code gen or outright bugs that happen. So this is a motivation. Is it UB? If you return the wrong ordering type, I don't think it's actually UB to claim that you have like a strong order when you have a weak order, but I'm not sure, honestly. But yeah. The motivation here is generally, you should, let's see, do I get to this in one of my upcoming slides?
Yeah, Roger got the question I was really asking, which was like, will std map or std vector misbehave if I have the wrong type of ordering?
My answer is I don't know offhand. They very well might. And my suggestion here is try very hard not to manually write spaceship operator things. So on this slide, we're showing what the preferred route is. And actually, this is what I've written everywhere but about one time that I've had to use spaceship, which is just defaulting it. So if you default this thing, you normally want to return auto. And auto means the compiler will deduce this, and it will deduce this based on the ordering types of the underlying implementation. So here, quiz question, what type do you think that auto will deduce to here under the hood? Yes, yes. Well, actually, no. Sorry, I thought of one of the two things. Yes, it's not weak. It's partial. This is a partial ordering because floats do not have meaningful comparisons across the whole range of elements. So here, operator spaceship is going to be a partial ordering. And if you later change the implementation to like use int keys instead of float keys, it will magically change to use the right type. How can the compiler know if the object can be distinguished using public methods? Well, the answer is for the basic types, they don't have public methods. So they're basically all either like strong or partial. For your own types, normally this boils down to, well, my result is the result of whatever my members are. And, you know, you keep chasing those back until you get to basic types. But if you do have to write something manually, then yes, like you do have to actually implement the correct operator spaceship return value. And the ones in the standard library do that. So if you're defaulting your spaceship, you should probably return auto. If you're not defaulting your spaceship, you should probably not do auto because you're doing something unusual. So you should explicitly think about it and write it. And then, yes, you have what Ellie mentioned, which is a maintenance hazard. Michael asks, what if you have multiple member variables? You get the weakest of whatever the members are. So if you have like strong, strong, partial, your overall result is partial. All right, so let's go back to this example from a few slides ago. If I return auto, what will it do? Is doing that correct? Yep, Robert and Julian have it right. It will, in fact, be strong. And in fact, this is weak. I don't think it's partial. Yeah, this is weak because the keys have a strong order. So that's what operator spaceship will do. But unfortunately, our value here, our value accessor makes this overall appropriate for a weak order. So this is an example of why you do this. So now some minutiae, and this is where I'm going to get back to eventually, all of the stuff about equals versus spaceship. But we've basically hit the major stuff. I'm now covering like minor issues that people probably have to care about it when they're actually implementing this in production, but are a little bit like outside the thrust of overall how things work. So when I overload operators, I can never remember if I'm supposed to use a member function or a non-member function. And I always end up going and looking this up on Stack Overflow. So here's my guidance to you on how to do this. For the common case, you should use non-members. And that's most conveniently done by writing a friend function inside your class declaration. Why? Well, the least satisfying answer is because the style guide says so. And if you're an authoritarian, that's enough for you. If you want rationale on why, part of it is because if you write a member function, you get something like the first prototype that I'm showing here. This is wrong, but it's wrong in a way that's not immediately obvious to a reader. What's wrong about it is that we forgot to write a const qualifier on the function, which means that effectively it's doing what the second prototype does, where the first argument is passed as a non-const ref instead of a const ref. The thing is, that second prototype stands out to me a lot more when I read it as like, wait, why did you pass sref and const sref? Why do they not match each other? Whereas the first one is easy to just fly under the radar. So if you write things as non-members, it's a lot harder to forget to const qualify because they just look weirder. And for heterogeneous comparisons, I personally recommend using members. Not only is it shorter, but if you write it as a non-member function and you write both arguments, people tend to forget that reordering can kick in and allow calls in the opposite direction, whereas the member version looks like it allows comparisons in either order. So I find the first prototype here to look more like what the code will actually do than the second, and that's why I advise this. Okay, now we had several questions on this. Earlier, I mentioned that defining spaceship does not auto-generate anything, and that it does not give you equals and not equals. I lied. So if you explicitly default your spaceship operator, and you don't do anything else, then the compiler will auto-generate something. Namely, it will auto-generate a defaulted operator equal. This is a little bit like how the compiler will sometimes auto-generate or auto-delete various like copy and move things when you start defining some of them. And the rationale here is that it would be very odd for a class to be comparable by inequalities, but not by equality. So if you defined the first one and you're defaulting it, the compiler just assumes like, well, you're not doing anything unusual, so I'll just conveniently add this for you so you don't have to write so much boilerplate. If you do not write equals default on your spaceship, then it will say, well, I don't know what's going on, hands off, and it will not auto-generate things for you. I think this is very unfortunate. To me, this is a mistake on the part of the standards committee because it's meant to save authors some effort, but it just muddies the waters about the relationship between these two things. Because people will write the first thing and then they'll be able to call operator equals like I'm showing down at the bottom with S1 and S2. And they'll be like, oh, okay, so all I do is write spaceship and it gives me all 6. And that's not what's happening. But what's actually happening is like confusingly similar to that. So this is why on the earlier slide, I said, just always write both, because then it's very clear what's going on and you're not relying on this extremely subtle and easily breakable behavior of the compiler. Okay, takeaways. If equals is meaningful, specify that. So if you can compare things for equality, then just do it. Do it as a non-member friend, at least for your homogeneous comparisons. Default it as possible. And for heterogeneous comparisons, you don't need to provide both orders. You can just provide one order and it'll work. Declare spaceship if you would have added less than or any of the other stuff. Again, as a non-member friend, again, default it if possible. Don't specify any of the other inequality things. Don't specify not equals, less than, etc. Just do the 2 primary operators as needed. And don't call spaceship manually because it's a big pain. It wasn't designed for that. It was designed to be rewritten to. Finally, nobody's actually audited the code base to remove all of the unnecessary operator definitions. So if you would like to do this, there is a migration bug, and it is linked in the slide deck. Finally, here is the TLDW of the entire talk on one slide. If you need to bookmark this slide deck and come back to this slide as your cross-reference, this is the cross-reference slide because I put the whole thing on one. So, I don't intend for people to actually read through this. It really is just literally a bookmark target. Questions. Now, I saw several things flying by in the chat as I was finishing off there, most of which looked at a glance like they were boiling down to, hey, you know, this really sucks compared to Rust. And I'm just totally not going to fight you on that one. I can only talk about what C++ is giving us, not whether it is giving us something as cool as other languages. I still think this is at least better than what we had before. So it may or may not be as cool as Rust. Let's see. Robert says, I'm a bit confused why a strong ordering couldn't imply equality support. So it probably can, I don't know, this is very much tied into the whole standards committee decision on like, hey, if you're defaulting your spaceship, we might as well just default operator equal equal for you. It's simpler to me when these two worlds are kept somewhat separate, but you are right that conceptually they are very much linked together. The whole concept of what ordering does a type have is very tied to whether you can do equality comparisons on any two particular things. And I can imagine a world in which spaceship, instead of being primary for the 4 inequalities, was actually primary for the 6 normal operators, and you only did spaceship and nothing else. I did not read the standards discussions enough to find out whether they considered that and why they rejected it if they did consider it, but that certainly would have been an option. Let's see. Julian asks, does it make sense to define equals in terms of spaceship? So this is kind of a different way of asking Robert's question, which is like, can you kind of boil it all down to just the spaceship operator? You could. Normally, I wouldn't, because spaceship is going to do a 3-way comparison on all of your members and all of your base things. And 3-way comparisons often have a less efficient implementation than the corresponding equality comparison does. I have written a couple of spaceship implementations manually for classes that have multiple member variables. And it's much shorter code to write like an equals comparison on that class, which is basically a single short circuiting call, than to write the spaceship one, which often has to explicitly like say, oh, it's less if this, otherwise fall back to doing the next one, otherwise do the next one, and there's like lots of conditionals in the code. So I would probably not choose to implement things this way. You probably can, it will probably work, but I wouldn't do it. Michael writes, can you expand on how spaceship equals default works with multiple member variables? I understood how it would choose ordering on least restrictive, but there are multiple possible ways of defining less than that seem reasonable and disagree with each other. So what I believe spaceship does is it does 3-way comparison in turn on each of your member variables in declaration order. If one of them returns something other than like equal or equivalent, it will immediately return that value. Otherwise, it will move on to the next member. So if you 3-way compare your first set of members and they say less, it'll stop and return less there. If they say equal, it will move on, compare the next one, and see what they do. And then only if you get all the way to the end and all of them are equal will it say equal. So this is very similar to like how std tie works when you're using tie to do like tie of ABC less than tie of DEF or something. This dependence on ordering of member variables is scary. Lots of things are actually dependent on order. If you want to be really scared, consider destruction and construction order and how it's often extremely important that we destroy things in exactly the reverse order of how they were declared, and we rely on that all over the place. Let's see, you could make it explicit how things worked by defining your own spaceship. Yes, you can. So it's longer and it's more error prone and it's a maintenance hazard, but if you want to do it that way, you can do it that way to be clear about exactly what's going on. Ellie has raised a hand.
Yeah, this might be a little too in the weeds, but if you go and read the documentation for these like comparison types, you find these fallback functions that are mentioned there, like std compare strong order fallback and stuff. Do we need to care about those at all or not?
I'm wildly going to stab in the dark and say no, because I am not even aware of those. So I would have to go do research to find out what they even are and how they work. And if in preparing for this talk I did not need to encounter them, then they're probably not that important. I will certainly look, because this is the kind of thing that I like to get nerd sniped about. So thank you for bringing that up, because that's a new one to me. Other questions? This is potentially the most sort of intellectual and arguably confusing of the 4 talks. Next week's talk is going to be all about templates, which might scare you, or it might excite you. I don't know. But hopefully it will not be that scary. We're basically going to show how to write good templates in C++ 20. So hopefully less like theoretical and defining vocabulary and stuff. Robert asks, what does the multiple spaceship operator implementation look like? Oh, a spaceship operator implementation for multiple variables.
Yeah, exactly.
I don't think I showed that. Let me quickly go back through my slides just to make sure I did not show that. This is really the only manual spaceship implementation I showed. There are at least some in the Chromium code base.
Are they ANDed or something, or?
Generally, let me see how fast I can use code search. Operator spaceship dot star squiggly brace. Minus third party. Always important. I'm looking to see if I've got, okay. So here is one. Oh, that's not terribly visible. So this one, as someone suggested, just uses std tie. So it ties together all the members and then just does a spaceship on them. This probably could just be done with equals default, because, oh no, wait, no, it's not, because the mask out key event flags calls here are making changes to the values that you get back. So it's not actually comparing the members directly, it's comparing a modified version of the members and then tying that together. So that's how this one thing does it. And then, let's see, are there any other obvious cool things here? This one also uses tie. It's looking at a subset of the members, and this looks potentially interesting. Oh, this is kind of cool. Okay, so this one is basically checking explicitly for an unordered case and returning that, and otherwise falling back to spaceship on a member. This is a very common kind of a thing. I've written this sort of thing where you have like, oh, this is explicitly some particular case that I return an instance of this for, and otherwise do some conditional set of things with spaceship on the members. So a lot of your manual implementations would look like this thing. I think with that, we're out of time. So thank you all for coming and listening, and hopefully I'll see you again next week.